Hello. I'm glad that you are here in such a large number. So we're going to talk today about the way of communicating in a microservice architecture. So who am I, first of all? My name is Irina. I'm an MVP for developer technologies, and I'm Romania-based, so I'm from Romania. I teach .NET, and I organize a .NET user group in our city called Yash. So thanks for having me today in here. So this is a short agenda we're having for today. We cannot talk about microservices without talking about monoliths, right? I mean, we evolved from monoliths to microservices. We're going to talk about HTTP calls, sync and async, and about RPC, and then we're going to talk about messagings. Messaging and pretty much three types of messaging, of using messages, like with queues, with message brokers, and actor models. Okay, let's talk about monoliths. I know it's kind of boring, right? Monolith, the stuff that it's self-contained, it's hard to deploy and so on, but who worked with monoliths? I could raise two hands. Right. Do you love monoliths? Yes. Yes, right? Pretty cool. I love them too, but I will tell you why later. So, a quick review. A monolith, it's self-contained. It's a single code base, which is very nice because you check out a single code base and you open a very large solution, like, I don't know, with 50 projects, maybe? You saw such thing? I've seen it. It's hard. And when you push 50 solutions, yeah, or projects, it depends. When you press build, you can grab a coffee, came back later, and hopefully your solution will be built, if you're lucky enough. But what's really cool about monoliths, because they are cool, is that you have a single deploy unit, right? So when it's time to ship in production, well, you need some luck, right? Time passes, the build takes long, right? Tests are running very slow because it's a single huge chunk of code. And if, God forbid, something happens in production and you need to redeliver a patch, well, you're in trouble. And then you start the process all over again. But let's face it, the life is easy for developers, right? I mean, everything you will ever need in terms of code, it's in there. You instantiate a new class, you new stuff, and it's in there, right? Or maybe, I don't know, inject it through dependency injection mechanism if you have it. But there's an easy life, right? Everything you will ever want is in there. But in monoliths, dependencies are in your code, and this is it. You do not depend on, I don't know, anything else. It's in there in a large box, and you manage it locally. But another thing with monoliths is that it's a single technology stack, right? If you're a .NET developer like me, you might love that. But there are business scenarios that require for you to have, I don't know, a component that runs in Python or in Go, why not? And a component that is in .NET or Java. And with a monolith, you cannot do that. I know .NET brags about its platform that it's interoperable, right? But not always the case. But in terms of deploy, is all or nothing. I mean, everything works smooth or it crashes gracefully, right? Not so gracefully, but it crashes. And the hell breaks loose in production. Okay, let's say you have a way of managing this, right? Maybe you have a load balancer with 2 servers, and you deploy on the first one, and then deploy on the second one, and you check stuff. But it's 0 or closer to 0 continuous delivery. And our clients don't like that, because the tendency now is to deliver faster, right? Improve and deliver features as fast as you can, because the businesses require it and the clients ask for it. And it's hard to test. Think about if you have, let's say, automation tests, I don't know, integration tests. It's not the case for a monolith, but you can run a suite of tests. But have you ever thought of your colleagues that are manual testers, and they need to do regression testing every time there is a deploy in there, or smoke testing and stuff? It's a hard life for them, but we do not care because we code, we ship that code to the infra guys, DevOps, and they take care of the deploys, right? It's easy. And we just wash our hands and our job is done. But in terms of scaling, because nowadays the data is more and more large, the storage is cheap, so the data is large. To scale a monolith, because I don't know, the business requires it and a lot of clients use that application, means to give a larger machine. A larger machine or more potent machine in terms of RAM and CPU. And this means scaling up. And with a monolith, you only can scale up. Scaling up means more money that our clients or our company needs to spend on infrastructure. So we have no choice but to give more resources to a machine, right? And this is the only thing that we can do with a monolith, only up, okay? I know, yeah, Docker and stuff right now, but what is the point of having a Docker image that has, I don't know, 8 gigs of memory? I mean, it's the same problem in there. You containerize that, but it's hard to deploy, right? So then you think, okay, I have a monolith, let's break that. And you think, okay, those are the boundaries, you can split it, right? Instead of a large solution, you can make small ones. And who worked with microservices? The bounded context and so on, right? Okay, that's pretty neat. Life looks easier right now, but it's not so easy. So a microservice is a thing that is not a monolith. But we'll see that microservices tend to be monolith. I mean, they love to, they have a memory, and they want to become monoliths as soon as the business develops. So it has its own database. You have that. I have that. OK. It's easy to deploy, right? Small, deliver it, and everything works just fine. It's standalone. I mean, it can function on its own. And it's easy to maintain, right? Yeah, it is. It's a small piece of code, self-contained. It's easy to maintain. Or is it? I mean, it introduces complexity, right? I mean, you not only have one large piece of code to maintain, you have multiple pieces of code to maintain, right? It's complex. It becomes more complex. And in case of failure, we have cascading effects. With the monoliths, we know it fails, everything fails, right? It's easy. But what about microservices? It's the same. I mean, if a service fails, maybe some other services will fail that depend on the first one, right? But with microservices, you need monitoring, strong monitoring. How do you do that? Well, analytics, logs, tracing, and maybe if you were lucky enough to run in cloud, you have something that cloud provides, right? App Insights, you can see everything in there. Maybe you, I don't know, implement structured logging, and you create Kibana dashboards, or maybe you introduce Grafana or something, and you have everything running on a desktop near your computer right there. But that takes time to implement. So, business concept and a microservice introduces a culture of automation. So, I mean, it should introduce a culture of automation. And it should be independently deployable to isolate failure. So, what happens if we have these components are independent, but as soon as the business develops and the requirements come, and our business analysts give us more to implement, we have loosely components, small code bases, easy to deploy and scale, reusable. Reusable is the keyword in here. But we have multiple databases. And what happens if a business scenario comes like this? That in terms of communication. You'll end up, I don't know, from this to something like this, because those are independent units that are used by some other services, and you get something like this. Well, you need those services to communicate in somehow. Actually, this is the Mozilla dependency graph from Firefox. It seems very nice to exemplify what I want to exemplify in here. So once you have these components, it's hard to manage their communication, right? Your goal was initially to make them independent, okay? On database requests, there are links to a certain UI, to a client of some kind. But as soon as those independent units need something from other independent units, your life goes not so nice, right? Because now you have so many options, and now you have so many things to monitor, and to watch, and to deploy, and to manage. And, well, you kind of wish to get back to that monolith, because there was only one monolith, not some multiple pieces, right? But if others can do it, you can do it too, right? So let's have a look at a few facts, like Amazon calls 150 APIs to build a single page. I mean, Netflix services around 5 billion API calls each day. And from those, 99% are internal. I mean, service to service. They can do it. Why couldn't you, right? I mean, those are giants, right? But if we take their example, it should be easy for us to implement the same thing, right? So the first thing that comes to mind regarding communication is to do some HTTP calls, right? Come on, it's the first step you think. You need something from somewhere else, you do HTTP call, right? A client, call them, you have the address, you get the response, and you do something with that response, right? So easy stuff. Because the S in there is a service, and the H is a handler, right? So the request goes like this. The other side processes it and sends back the response. And you're happy. But the happiness doesn't happen every time, because you might have something like this. When the handler processes it, but it doesn't send the response back, for whatever reason. I don't know, you have a latency, or the handler is down. Then you cry a bit. And you cry a bit and don't even know that the request has been there. So, in the next slide, I've recorded my screen to show you. I hope it's intelligible enough. Here is a HTTP call made to another service. It's in .NET Core. It's a little bit slow, but hang on. The problem with HTTP calls is that if the first call fails, there is a big chance that the next calls will fail too. And you won't be able to trace those calls. I mean, we're not talking about a client like a UI application written in React or Angular or Vue or something that calls an API to get data. We're talking about internal communication. So what happened was that the first request failed because the handler is closed. Okay, so I get from one hand to the other hand, and the other hand is closed. So there is nothing to receive a request in there. So it failed. What was the request? What it was contained in the request body? Well, you don't know. Because some might say that it's perfectly fine to use HTTP calls between services, internal calls. But how about timeouts? How do you manage that? I mean, you make a call and you wait for an answer. How long do you wait for an answer? You must think of something. I mean, you cannot wait indefinitely, especially when it is service-to-service call. How about availability? How do you know that the party that you're calling, it's up and running to process your requests? You don't know. You monitor, but you need to manually intervene there, right? We broke the monolith just to make sure that we decouple stuff. We broke the monolith to make sure that we have independent units easy to manage. But if you use HTTP calls between services, you're going back to coupling. I mean, right? There's a contract on the end, one end, and that contract should be the same on the second end, right? The receiver and the publisher. And you can lose requests, and you don't even know about it. If we're talking about, I don't know, the client side, then you can force somehow the user to refresh the page, hoping that the response will come to him, right? But in a service-to-service call, you cannot force anyone to do the requests. So you need to implement a retry mechanism by yourself. Of course, sure, you're going to tell me that Poly is a library that takes care of that, if you're in the .NET world. But it's kind of not so easy to implement, right? So some might say that it's perfectly fine to use async calls to distribute load, right? You're not waiting for an answer. That answer will come at a certain point. But you will have exactly the same issues as in sync HTTP calls. But you can serve more requests, apparently. And you can serve a request faster. It's not real, it's apparent. But let's see async. So what I'm doing here is a call to an API and not waiting for a request. And you're going to see that, well, apparently I can push many requests from one side to another. What I did in here is to take a time span of 20 seconds and to do as many requests as I can in those 20 seconds, sending an I that increases in size. That's what the numbers represent. And I did that to all my demos in here just to see how those are comparable. So 20 seconds, 3,500 requests, right? But the problem is that on the other side, I don't know if someone listens. I mean, I just fire and forget some requests. And this is it. So let's talk a little bit about HTTP, because it's the go-to protocol when we're talking about web. So HTTP is sync by nature, right? It's a synchronous operation, because you're issuing a request and you're expecting a response to that same request. What happens with HTTP is that it opens a new TCP connection for each one, which is kind of costly. There is that DNS lookup for each request, right? There is network latency, right? And those things add penalty to your application. So you have no retry out of the box. You cannot specify, HTTP doesn't specify how many times you should retry stuff. You should go in there and implement the mechanism by yourself. No delivery guarantees. So you don't know that your request reached the requested endpoint. You don't know that. So you have no routing without a service discovery mechanism in terms of microservices or configuration. So there is no location transparency. You need to specify each endpoint that you're going to call in your applications. So for each dependency graph, each microservice should have an endpoint. And those endpoints should be manageable and managed somewhere. Of course, if we're talking about cloud, there's that API gateway, there are registered endpoints, and it's easier for you to manage them. But with tens of microservices, there is an issue to manage those also. So HTTP requests are good for public-facing APIs. Okay, so you expose an endpoint and you leave someone to make the request in there. And for us, our familiar is the go-to approach, and they're easy to debug. I mean, it's an endpoint, call that, even in Postman or in browser, and you'll get a response based on your request. But the challenge is, when talking about HTTP requests, is that the service discovery needs to be implemented somehow. You need to tell those consumers that you have some endpoint that can be called to get some data, right? Retry policies are not so easy to implement, and you need also circuit breakers. So these are patterns for fault tolerance. So let's say you enforce your API to retry a call for 5 times, and if you don't get an answer, you need to short circuit the stuff. Okay? So timeouts, the same. That's a challenge. And the routing, and the tracing, okay? And if you're willing to face all these challenges, then you should go for HTTP. And if you're ready to accept everything that is not okay with HTTP calls between microservices. But let's talk a bit about RPC. Who heard about RPC? That's cool. So this RPC I'm going to talk about is made through a queue, through a rabbit queue. So it's pretty much a kind of API call, right? Because you need to know the endpoint somehow. But it's done through a message broker. What is nice about it is that the system somehow preserves encapsulations. And it's a way of calling something through another system as if it were in the same system you're calling it. So it kind of looks like it. You have a queue, you send a request in there, you have a handler to the other side. The handler takes that message from there and processes it and sends back a response through the same queue. Okay? So in the next slide, I have a demo that hopefully will run. Okay, does something. So I have a server and I have a client. And the server waits for RPC requests. And the client makes requests. Okay, so asking a question. It's the same scenario with an I sent to the other side. And you're going to see that in this case, we're going to have a lot more requests made than in HTTP calls. So we have 5,000 and something messages sent compared to 3,000 with HTTP. So in this case, we are able to process more, right? And in the next slide, we have the same scenario, only but with Fibonacci. Okay, so the client sends an I, and the server computes the Fibonacci number for that I, and sends back the response. Come on, sorry. I mean, the videos are making fun of me. Okay, so we have a connection. This is the server that creates a queue and responds to an event when something gets through that queue. Parses the message and computes the Fibonacci number in that. Okay, so the basic formula. Don't judge me for that. Okay, and the client pretty much for 20 seconds should call an I to the client to get a response. Okay? It should run. So what happens in here is that we have two systems that act and call things from one another as if they were in the same system. So if we're talking about queues, we're going to see an answer for about 40, I think. And as you see, those are pretty large numbers. Yep, and it's kind of going to stop. It's easy to use, and you don't lose requests. I think this is one of the most important property of using a queue. You don't lose the requests. You can add more handler instances. I mean, if you need to process more, you can spin up a new instance of consumers, and you'll process more, right? Faster. So you apparently spread the load. You do process more requests as in HTTP. But the deal is that RPC is sync. You send the request or a message in our case. That message is picked up to the other side, is processed, and you get a response back. And you didn't solve pretty much than, I don't know, making more requests. A little faster, but it's still sync. I mean, your system won't be able to process, I don't know, super large amount of requests. But it's way better than HTTP. Okay? So let's talk a bit about messaging. What is messaging? It allows you to integrate systems. In our case, microservices. And it doesn't require both systems to be up. I mean, you can send the requests or messages from one side, and the other side can be closed. You won't lose anything. What will happen is that whenever the other side will wake up, you're gonna process the requests, right? Or the messages in our case. What is a message? Message is pretty much has a header and a body. And the header has a few properties, exactly as in HTTP requests. And it's done through a queue or a certain mechanism, and we're gonna see what the mechanisms are. So these messages trade consistency for availability. I mean, if you have a system and a business scenario that requires you to have pretty much everything, not to lose anything, use a messaging system. Because, I hope it's gonna work. Okay, this is RabbitMQ. And this is the same time span. I'm gonna show you pretty much for 20 seconds how much messages you can push through that queue. And we're way past HTTP and RPC in number. And 20, 26, okay, I cannot pronounce the words that fast. But as you can see, it's pretty much an improvement, right? 38,000. And fun stuff is that those are there. Even if our consumer is closed. So every message we send is in there and available for you to pick up whenever the party will wake up, right? So it's very important because you cannot lose requests in some businesses. And if you need to process those 38,000 requests faster, you just spin up 3 consumers and you get the responses for that. So those are the main principles of messaging. But let's see about async queues. So we have that sender, we have a queue, and we have a handler. What means async in this case? It means that you'll pump requests in a queue. And from that queue, a handler will pick them up and send back the response to another queue. And from the other side, the sender will get back its response. It's pretty nice, but you need to model your data to support this scenario, right? Because your data and the messages you're building need to be independent somehow to be able to send as many as you can in a queue, to allow a consumer or handler to pick them up from there, and then the handler to put the responses in another queue to be picked up. So This is pretty basic, but how about a scenario when you need to process something from a queue and then store it in a database? Well, you have an issue. Because, well, even if you're processing them async, the database is a system that is not somehow async, right? We indeed can process more requests faster, we don't lose them, but we kind of move our problem to somewhere else, like in our case, the database. Well, connection pool is scarce, is limited, right? So we need to do something about it. So in some cases, we need to batch process the messages. I mean, if you know that our connection pool supports 100 connections opened, then we should pick the messages in batches of 100 to be sent to the database. So if we ever process more and more and more, and the bottleneck is our database, we need to use a semaphore, and the problem adds up. So, to summarize, why should we use a message broker with microservice architecture? Well, because we can become more agile, we can develop faster. There is no integration process. I mean, we don't know, like in HTTP, we don't need to implement a retry mechanism and every pattern that we know, just not to lose messages. Teams have ownership and a full understanding over those APIs they develop. And if needed, we can definitely switch technologies. I mean, we can have a .NET API that sends a request through a queue, and on the other side, the consumer is something that is written in Python or in Java. There is no problem, as long as the integration point is technology agnostic. And pretty much we're using like byte arrays or JSON to make exchanges of those messages. So, resiliency. So you don't have a single point of failure right now, or multiple points of failure, as in microservices with HTTP calls. You basically leverage that system to take care of everything for you, push the messages through queues, and you will only take care of the consumers from those queues. Scalability. So if with monoliths we could only scale up, with microservices we can scale out and up. I mean, we have two axes where we can scale. So we can either add more RAM and CPU to certain microservices, or we can either add more instances of those microservices. And if we're talking about consumers, we can spin off more with more RAM, and then we'll be more performant. So we have two axes where we can scale. Okay, performance. How performant can we be? You saw that we had a large amount of requests processed by our queues, right? So we all want performant systems. Or if we don't want, our clients definitely want those, right? So performance, in a way, comes from increased throughput. I mean, those numbers. The first large one is using a message broker, like Rabbit. And the second number is using HTTP calls with the same scenario, with the same 20 seconds time span. So I think it's a way improvement, right? If we do a proportion, it's 10 times faster, 10 times better throughput. So elasticity. With microservices and the way of communicating and the usage of a message broker, we can scale up and down as like the cloud, right? We'll only have that system that will process the messages for us, and you'll spin off more consumers if needed. But this is it. We're talking about elasticity here exactly as the cloud, but having our system on-premise. If we have the cloud, then we're happy. But not everyone has that infrastructure available for him. So, a lot of utilities because there are a lot solved by microservice architecture and the usage of messaging. So reliability, we don't lose absolutely anything. So flexibility allows us to have systems in different languages, and this is flexibility. Distribution, we can have microservices running on different networks, on different servers. We don't need to have everything on the same machine to be able to process. Distribution, increased throughput. You saw the numbers, 10 times better. Scalability, so we can scale better, you can process more. We can scale up and we can scale out, okay? It's elastic. We can scale only what we need from that system, not the entire block. So this goes with an implication, decreased costs, okay? Performance, and we really love that on a system. And agility. I mean, think about it. Bringing a junior in your team, right? If you hand him over a monolith, it will be very hard for him to understand everything that's in there. And moreover, a monolith might have a lot of functionality that is, let's say, not known, even by the senior developers. But handing over a microservice to a junior dev, it's way faster for him to get up to speed with the development and to make him owner of stuff. And in the end, the junior will only help you in development. Okay, what tools and frameworks and systems do you have available? Well, these tools and frameworks and systems, also called messaging middlewares, or have different terms depending on the book you're looking at, are of three types: queues, actor model, and message brokers. So these are the three types of message middlewares. So what options do we have? And others, but I think these are the most important ones. RabbitMQ, ActiveMQ, Kafka, Mass Transit, ZeroMQ, and many more. But these many more systems are split into three categories. So, queues. And a queue is used for point-to-point communication. Like we have a sender or an API that sends a message through a queue, and the other side receives it, processes it, and maybe, I don't know, sends in another queue and so on. Basically, queues are the easiest and the simple tools that we can use. I would mention here Azure queue can be used here, Amazon SSQ, and many others. You can even implement one in memory if you want. It's easy, right? It's a first in, first out distribution. And pretty much there's a pull mode. If we're talking about messaging systems, we have two modes, push and pull. So basically the receiver in here pulls the message from the queue. Okay, the message is not pushed to it. It asks, okay, there is a message for me, there is a message for me, and pretty much this is the pull mode. Actor model. It's pretty, let's call it new, but the first theory about actor model, it was written in '74 on a doctoral thesis. Pretty much everything it's an actor in this model. And one example is aka.net, because I'm a .NET, but it's aka for Java. So from what I've seen, an actor model is pretty much an object-oriented approach where you take care of the way the messages are consumed, so pretty much the consumers. You can create children from an actor, and you can supervise children created, and everything works pretty much as a graph inside an actor model. They say that it has a higher abstraction for concurrent systems, and it takes care of a lot of messages in few gigabytes of RAM compared to other systems. Can delegate and create new actors, and it's a higher abstraction of everything that is the messaging system. You can use it like independent or with Rabbit or with a queue. It's your choice, and it depends on your business scenario. Message brokers are the easiest way to work with messages. So basically what happens in a message broker, you have one process that sends a message to a named queue or topic, as you're gonna hear in Azure. You can have one or many consumers for the same topic or for the same queue. It handles for you the connections and disconnections. So you don't need to care about consumers if they are connected or not. This message system will take care of that for you. It's one-way data flow, or you will hear more often the request-response model, where you also specify in the header reply to implement that RPC. There is a dead letter queue concept. So if a message is not processable, you have the option to send it to a dead letter queue, or the message broker will send it for you there. So you can set all kinds of properties, like how many retries you use for that message. For example, you try to process that message 5 times, and the 6th time it will go to that letter queue, because otherwise it will only be requeued, right? So ActiveMQ, Rabbit, and Kafka, and NATS. For example, NATS is used by Siemens, Pivotal, and VMware to process. Rabbit is widely used because it's open sourced and it's old. And it uses a different protocol than HTTP. And I'm going to talk a bit about RabbitMQ, for example, because it's lightweight. The queues are first in, first out, and supports AMPQ protocol. And it's fast and easy to use. And it has a principle that is called at least once delivery. So at least once means that a message will be sent to a consumer at least once. And it depends on you how you treat that dissemination. Okay? So, for example, a message broker, or AMPQ in general, it's used by the Ocean Observatory Initiative to process and collect 8 terabytes of data per day. I mean, it's huge. JP Morgan uses AMPQ and something similar to Rabbit to process 1 billion messages a day, which is huge. I mean, it's clear that it's very useful for them. So AMPQ is a protocol used by certain messaging systems that is async by nature. It has a guaranteed message delivery, and it has at least once, exactly once, and at most once delivery. So pretty much every scenario that you can have with a message delivery. The deal with AMPQ is that it has no DNS resolve. The routing is programmatic, and it has retries out of the box. You don't need to do those. So you have acknowledge, not acknowledge, out of the box. You, depending on the business scenario, you can acknowledge or not acknowledge a message programmatically. For example, if a message comes to processing and it doesn't, has something that you need for it to be processed, you can manually call acknowledge, and then it will be removed from the queue. Or you can call not acknowledge, and it will be requeued. Okay? So the deal with AMPQ is that it opens one TCP connection, and it has a concept that is called a channel. And that inside the TCP connection can be a multitude of channels that handle communication back and forth. And this is why we saw that tremendous increase in throughput when using messages and Rabbit, because there was only one TCP connection, and inside that connection, a multitude of channels. So abstractions inside the same connection that travel the information back and forth. So it's useful to use AMPQ. So what do we have? Options. We can have direct exchange routing out of the box. So to the right side, we have consumers, or we can call them microservices, that are interested only on the routing key that's on the line. So the first message, the first queue is interested only in images.archive if the message contains that routing key. And the one below, it's interested on images.resize. And at the end of it, we have a resizer that I think pretty much will get a path or to resize an image. So this is done out of the box. You can listen to whatever topic you're interested, okay, in point-to-point communication. Another thing is that you can have out of the box fan-out. Or fan-out is a concept that you'll find in different message systems under a different term. But pretty much you have a message that will be broadcasted to every consumer you have in there. And it depends on you if you process the message or not. Okay? And then you might have an issue with competing consumers because multiple consumers will try to process the same message. And topics, you can add stars like pattern matching for each topic. And at the end of the queue, you'll have something that will be interested in that specific topic. So, for example, I don't know, maybe you're interested in writing logs. And those logs have a priority, like, I don't know, high priority, medium, and low priority. And then you can spin off consumers to listen only on what the topic you're really interested in. So this is a very powerful scenario. And I have in here 2 books that are pretty much a must-read. In enterprise integration patterns, you'll find a lot of terminology that is the go-to Bible for messaging. And designing data-intensive application is the same, a go-to Bible, the second Bible. Just because the challenges nowadays is to handle data that is more and more and more. So we need to know how to handle lots of data. And go to these books because those are really helpful. So in summary, I want you to remember that HTTP works, but it's not reliable. And with HTTP, you open a new TCP connection for each request. With messaging, you don't. So using a message system allows you to process more, to increase your throughput, and to be more reliable, and to obtain a lot of utilities that are really important in the business scenario. So messages are pretty great. So show them some love. So don't run of messages. It's hard to switch your mindset towards messaging because you need to model your data in a different way. But in the end, it pays off. So don't run of messages.